Oh. Now thinking the same thing.
Okay, let's go ahead and get started. I hope, let me know if you can hear me okay on Zoom. I'm trying this new microphone out and I think it works, but I'm not certain. So if you see my lips moving, but you don't hear anything, say something. So same applies out here too. So, okay. Any questions on anything so far? Okay, that's good. And if you're cold, so am I. I can't do anything about it. That side of the building has the heat. We've got the cold. So short of building a fire somewhere inside, which they probably wouldn't like. We'll have to bear with it. So anyway, we're talking about chemistry. We got as far as solutions, and what I want to do is go back here and go into, open up this slide here on solutions. We've gotten into mixtures, and we're talking about chemicals and molecules and stuff like that. And one of the points I made the other day was that there are two ways that substances are formed. There are chemical reactions where the end results are changed from the reactants. The stuff you start with is changed when it's done. Like if you bake a cake, and I'm on sketchy ground here about baking a cake, but if you put all the ingredients together, the eggs and the flour and the sugar and whatever, and you bake it, you apply energy to it, that's a chemical reaction. And the cake product at the end is totally different than what you started with. You can't see the eggs or the flour or anything else in the cake. That is where we have a physical change taking place. But the other way we form substances is through just mixing it together where there is no physical change, where you can actually separate out the components, regardless of how well they're mixed together. And so one of the simplest ways of a mixture is a solution. And we use solutions in healthcare all the time. An IV line is a solution. You have an IV. If you've ever had an IV, for whatever reason, it's a percentage. It's a simple solution, and it's usually measured in percent. And that's the easiest way to keep track of a solution. What percent of it is? What percent of it is the substance dissolved in it, the solute, the salt, the sugar, whatever? What percent of that is in the water? Because most IV lines are based on water, and you get a 5% sugar or a 0.9% sodium chloride solution, which is the same salt concentration as our bodies. It's very, very simple approach. As I said the other day, if I take a 1 liter beaker and fill it with water to the 1 liter mark, I have 1,000 milliliters of water. If I add 100 grams of salt to that, I now have a 10% solution because of salt, because 100 is 10% of 1,000. You don't get hung up on the milliliters and the grams, and just take the numbers. And 100 is 10% of 1,000, or 400 is 40% of 1,000. One of the experiments we occasionally do involves a 40% glucose solution. So we mix up 400 grams of glucose in a liter of water, and now we have 40% glucose. It's very easy to process, to understand. You don't have to do a lot of calculations if you make up a solution like that, other than measure out the solute, measure out the salt or the sugar or whatever. Well, that's the easiest. The second one I said the other day is milligrams per deciliter. And we use that. It's a pretty important mechanism that when we measure things like our blood sugar. So when you have blood work done, and this is something you can't usually do at home. Well, I guess you can with if you have a patient that has diabetes and they're measuring their blood sugar, the little handheld devices do that for you and tell you that what percent, or what the magic number you're looking for, because it's always assumed that it's milligrams per deciliter. A deciliter is 1/100th of a liter. And instead of having to do the calculations and trying to comprehend what that means, the meter tells you your blood sugar is 90 or 200 or whatever it is. And even when you're charting, it's generally, it's assumed that when you have a number for blood sugar, it's going to be in milligrams per deciliter. And it's, again, pretty straightforward. We use the same value for measuring red cell and white cell concentrations in our blood. We don't have to worry about knowing the units because it's assumed that it's milligrams, or number per milligram per deciliter or something like that. Now, the third one, this is where I stopped the other day on molarity. Molarity is the number of moles of solute per liter of water. Now, that's sort of a circular definition there, but a mole is a very simple calculation. If you add up the atomic weights of all the atoms in a compound, in a molecule, that would give you its molecular weight. So for example, sodium chloride. Sodium has, let's see, it has an atomic weight of 23, and chloride has 35. 23 and 35 is 58, I think. Yeah, 58. Okay, so, and all I did was look at the numbers at the bottom underneath the simply. There's sodium chloride, table salt. Sodium 23, chloride 35. The combined weight of the two atoms is 53. Now, if I want a 1 molar solution, I don't know why I would, but if I wanted a 1 molar solution of sodium chloride, I would take 53 grams. I take the molecular weight and convert it to grams. I just say, okay, the weight of the two atoms together is 53. The weight of the molecule, that means the weight of the molecule is 53. That means if I have 53 grams, I have a 1 molar solution. I have 1 mole of salt. We don't usually talk about table salt. I want to go buy a mole of table salt and from Morton's or whatever. We don't look at it like that. Chemists would though. So we would add, if we wanted to make a 1 molar solution of table salt, we'd use 58 grams of sodium chloride in a liter of water. If we want to make a 1 molar solution of glucose, glucose weighs out to about 182. Already did the math in that. So, but it's just the 6 carbons, 12 hydrogens, 6 oxygens. You add up their atomic weights, you get the molecular weight, convert it to grams, and 180 grams of glucose in a liter of water gives you a 1 molar solution of glucose. Now, where you would see this in chemistry, usually we pay attention to, this is how we pay attention to measuring the strength of various acids. A 1 molar solution of sulfuric acid or a 6 molar solution of sulfuric acid. What that means is that as the molar number goes up, it becomes more concentrated. So if and when you take a chemistry class, you would see that the more powerful acids are measured based on their molarity. So now, why do we care about a mole? Chemists get really excited about it. They actually have a day in October that they call mole day. They really do. And most chemists have, a lot of chemists I know have little stuffed toy moles. I'm not kidding you. Yeah. We don't have anything like that in biology or anatomy. We just got body parts. So, but a mole, and this is what's really unusual, a mole of any substance glucose or sugar or sucrose or salt or anything has the exact same number of atoms, of molecules in that mole. So a mole of sugar, glucose or sucrose, with two different sugars, a mole of salt will always have 6 times 10 to the 23rd molecules. That's a lot. We'll always have the same number of molecules. So it doesn't matter if I have a solution of sodium chloride, if I have a solution of glucose or a solution of sucrose, the number of particles in each one will be exactly the same. And they call this Avogadro's number. Because apparently this chemist years ago calculated all this out. I don't think he had much of a life, but you know, we don't know. Now, why do we care? Well, the reason we care is those molecules count as solute particles. Salt, glucose, sucrose. Movement of water across the membrane depends on the amount of solute and the amount of solvent in a solution. And so depending on the number of solute particles, that will dictate which way water will go. So we pay attention to this, and you need to remember Avogadro's number is 6 times 10 to the 23rd, and it's based on a mole, and that's all you got to remember. So, because I don't think anybody has ever come up to me and said, hey, well, what about Avogadro's number? What do you think about that? You know, that's never happened. And of all the people that I've sent through healthcare, none of them have ever come back, hey, you know, I'm really glad you told me about Avogadro's number because we were having a discussion about that just the other day. Not going to happen. So, but it does explain how, you know, where the solute particles come from in solution. So that's the I saved that special just so we could talk about that first today. So now a colloid, what's a colloid? Well, if you've ever had milk or cream in your coffee or eaten ice cream, you've been exposed to colloids. A colloid is also called an emulsion. This is different from a solution. In a solution, solutions are transparent. You can't see the particles floating in the solution. You can't see the sugar in the tea. You can't see the coffee in the hot water. It's there. Colloids, you can't see through. They're cloudy. They look thick. The solute particles in here are so large that they make a colloid like milk. It's what we say opaque. It's not clear. You have fat floating in the milk. And milk is made of water and butterfat and sugars floating in solution, and we can't see through it. And it won't settle. It won't settle out. It won't settle out. The most that will happen if you have whole milk, you know, unpasteurized, unhomogenized whole milk straight from the cow, the most that would happen is that the butterfat portion would tend to migrate to the top of the solution. You know, the old expression, cream rises to the top, well, that's based on, you know, milk right out of the cow, because the butterfat is always going to be, it's not going to mix with water. It's going to come to the top. It's like if you have a oil and vinegar and you shake a salad dressing, you shake it up, what happens is oil will eventually form a layer above the vinegar and the water portion of it. So a colloid never settles out and you can't see through it. And so there's your solution there. There's your colloid here. Jello is a colloid, even though it is somewhat transparent, but the solute particles in there are never going to settle out in there, and A jello can be somewhat transparent or opaque, depending on what color the dye is that you use. The third category of a mixture is a suspension. Suspensions will settle out over time. They have lots of solute particles in there, and if you leave them alone long enough, it will separate, they'll separate out. Blood is a suspension. If you take a sample of blood, like whole blood on the left-hand side on the screen there, and let it settle for several hours, the red cells will sink to the bottom of the test tube. The white cells will settle on top of the red cells, and then the rest of it's going to be the plasma. The plasma is about 55% of whole blood. It's just salt water. Or you can stick it in a centrifuge and spin it down in 5 minutes. But you'll get the layers. Things will settle out. Like in a suspension, things settle out over time. They don't go into solution. They don't, there's no physical change to the properties. They'll just settle out. You know, again, like when you have if you have an Italian salad dressing, you have to shake it up, right? You know, and when it settles out, all the seasonings tend to drop to the bottom of the bottle. The oil goes to the top, and then shake it up again. Certain medications that you have to shake, you know, it says shake well before using, because it has separated while it's in the container. Suspensions will simply settle out. The example on the screen here, sand and water. You know, you're setting up an aquarium, and so you put your sand in the bottom of the aquarium, and you pour your water on top, and the whole tank becomes cloudy. Hopefully your fish aren't in there yet because they don't like that. But it gets cloudy, and after a couple of hours, it's clear because all the sand has gone to the bottom of the aquarium tank where it belongs, and then the water is clear. Or you run it through your filter and it does the same thing for you. But you know, things like that, that mixture doesn't, you know, it doesn't stay cloudy. You know, a fish tank doesn't stay cloudy because the sand, the gravel will all move to the bottom, and all the dirt and debris will go with it. So these are the types of mixtures. We can have suspensions, we can have solutions, we can have colloids, even concrete, you know, or cement would be considered suspensions, because the sand and the gravel that goes into into concrete could be physically separated out. You could break apart the concrete and get it down to the individual. You could eventually break it down to where you could filter out all the components to it. There is no physical change to the property in concrete or a cement block or anything like that. You can break it apart, and you can still get the original components. Mixtures can always be separated, given the right kind of filter, because there is no chemical change in a solution or an emulsion or in a suspension. Red cells in blood are still red cells. White cells, and you can just barely see, there's a very thin white layer on the slide right there, right above the red cells. Those are the white cells. That shows you how I use this a lot, this particular slide a number of times in AP2, but it shows you that the white cells, there are so few white cells in a sample of blood, it's mostly red cells. We actually call that layer the Buffy coat. So because it's you know, it's all the white cells in that sample. So, but they don't, nothing happens to them. Nothing happens in a suspension to the ingredients. So in our bodies, now we'll take advantage of mixtures all the time. We use, you know, we eat and drink molecules. You know, we eat things that are going to be mixtures. We'll drink things that are mixtures. If we like tea, if we like a Coke, anything that has material in it that has not been changed, we will go ahead and enjoy that. You know, if you have a Coke, for example, you're going to get the sugar from the high fructose corn syrup. If you like tea, you'll get the sugar flavor in the tea. You know, the creamer in the coffee and the flavoring in the coffee or whatever we put into it hasn't been changed just because it's in with the coffee. So there is no chemical bonding going on. The creamer that goes in your coffee is still creamer. It hasn't changed. You could filter that out if you wanted to. Yeah. We do. We can do that. You know, there are very simple filters that you could buy, you know, for hiking and backpacking and camping. Water filters. You just, you know, life straws. If you ever heard of those, you can, you know, suck water out of a ditch, and it'll be fine because it cleans out the bacteria and the viruses and all the dirt and debris. You know, once you get over the idea of sucking water out of a ditch, but that's a different story. So we can filter this stuff out, because since there's no chemical change to things in solution, we can separate it out. But compounds are different. Molecules are different because they've had some sort of chemical change that took place with them. They are no longer something that can be easily separated. You can't take sugar and filter out the carbons and the hydrogens and the oxygens. You can't take salt and filter the sodium away from the chlorine. We can't do it because there's been a chemical change to the properties here. It's not like concrete or sand or soil where you can just run it through a sieve, a series of filters and well, here's the gravel, here's the sand, here's the dirt, whatever. So compounds are, as I say, homogeneous. A compound all looks the same. You look at glucose, you know, a container of glucose, and it all looks the same. Table sugar, salt, they all look, all the parts of the sugar are identical. Little white crystals, same with salt. Little white crystals. You can't look at it and say, oh, well, that's different. You know, oh, look, there's some carbon, there's some hydrogen. It doesn't work that way. We can't even tell the difference between sucrose, which is table sugar, the stuff, you know, comes in the bags and in the little white packets and stuff, and glucose, because they look the same. They are identical. They taste the same. They both taste sweet. So how could you tell them apart? You can't, because they look, they are homogeneous in appearance. The only way that molecules can form is through chemical reactions of some sort, and we create bonds between the atoms. We have chemical bonding. That is the point to where I'm going with this, so just sort of bear with me. But chemical bonding is how the atoms are held together to form the molecules. The chemical bonds involve energy, and energy is very important to us. We can store energy in the chemical bonds. When you eat a Snickers bar or an apple, you know, give you both sides of it, or anything, when you eat anything with calories in it, the calories, the energy that you get from the food that we eat is held in the chemical bonds that hold the atoms together. And the way that most molecules do that is they will try to share or manipulate their electrons. They will try to share or manipulate their electrons. The electrons have the negative charge. Now, so why are we worried about electrons? Because they're the only ones that are not only subatomic particle, not in the nucleus. The nucleus is held together is holding the protons and the neutrons together. They're glued together with, subatomic glue, which is pretty powerful stuff. We can't do anything with them, but we can use the electrons. We can hold molecules together by sharing electrons or stealing electrons, which they do, or giving up electrons, or sort of attracted to positive and negative charges from the electrons. Because if an electron's present, it's a negative charge. If the electron's not present, then you have a positive charge. That'll make sense here in a second. Okay. Electrons take up space around the atom, around the nucleus of the atom. Electrons are going to take up a lot of space here. And they're found in shells in orbit around the nucleus. Like the solar system model I showed you the other day, the planetary model. You got the nucleus of the atom in the middle, and you have electrons around the outside. And electrons are going to spin around the nucleus in a series of orbital shells, each one a little further out than the other one. And those shells are made, the distance from the nucleus, the further away you are from the nucleus, the more potential energy that these electrons can contain. See, because electrons are in orbit around the nucleus, and if you're in the first shell and you're spinning around, you're spending all your energy trying to keep from getting sucked into the nucleus. Because the nucleus is big. It's big and it's positive, and there's like a bunch of positive protons together. I didn't make that positive proton, but there's a bunch of protons together in the nucleus, and they're all positive. And here's this little itty bitty electron going along, trying to keep from getting sucked in. And it's going around at the speed of light. And it's all it can do is to keep from getting sucked in. But if you're in the next shell out, you don't have that problem. You're further out here. You can go around the nucleus, and yeah, it's a pretty powerful pull on you, but you're out here. You don't have to spend all your energy trying to fight the nucleus. You have stored energy. You have potential energy to do something. And if you're in the next shell out, you have even more potential energy. And so electrons are the source of our potential energy, which is why we use them to make in chemical reactions. So what do you need to remember right now? Well, the first shell of any atom can only hold 2 electrons. Got to remember that. The second shell can hold no more than 8 electrons. And the third shell, which is as far as we have to be concerned with, and then only for a couple of atoms, is up to 18. It's either 8 or 18. But no more than 18 in the third shell. But the only thing we talk about with the third shell is chlorine and sodium chloride. That's all we pay attention to in the third shell. So anyway, 2, 8, and 18. That's what you got to remember from this slide. 2, 8, and 18, the first 3 shells or orbitals. And it looks something like this. There's your first shell holding its 2 electrons. It looks a little crowded there, but there's only 2 electrons in the first shell. The second shell has no more than 8. And the third shell can have up to 18. Now this is, let's see, what is 13? That is aluminum, okay? It has 13 protons and 14 neutrons. I'm reading it off the screen. I don't know it by memory. But it has 13 protons and has 13 electrons. And so you have 2 electrons in the first shell, you have 8 in the second shell, and you have 3 in the third shell. You'll always, if you have 13 electrons, you're always going to fill up every shell that you can. With 13 electrons, you can put 2 in the first shell, because that's what it holds. You can put 8 in the second shell, because that's the max it'll hold. That gives you 10. 3 more electrons to play with, they go in the third shell. So, and that's what an aluminum atom looks like. And, moving a whole lot slower than they really do. Now, what does that mean? Well, it means that the first shell is stable. That very first shell is stable. It has 2 electrons. It means the second shell is stable. It has 8 electrons. It means that the third shell is reactive because it's not full. Atoms want to have their shells filled up. They want to be stable, and they will do anything they can. They will react with other atoms to achieve stability. We call the outer shell the valence shell. And the valence shell is where all the potential energy is located. The bulk of the potential energy is located in whatever the outer shell is. If it's only, if it's only the second shell and there's only 1 electron in the second shell, that's still the valence shell. Hydrogen is the only one that has its first and only shell as its valence shell, because hydrogen only has 1 electron in here. So typically, we pay attention to the valence shell. We see how the electrons are moving. We know that the outermost shell, whatever it is the valence shell, and that's where our potential energy is located. And we also know that atoms want to fill up their shells. So there's a rule of 8. They always want to, an atom always wants to have its electron shell full, its valence shell full. And even though it says 8 electrons in their valence shell, and I know that some have can have more than 8, that's fine. We're just going to deal with 8 because we don't really go past the bigger atoms. If you don't have your shell full, then you are reactive. If you have, like aluminum had 3 electrons in its outer shell and it's not full, it's reactive. It will react with other atoms because it wants to get stable. It really wants to be stable, it wants to have its shell full. And it will do whatever it can to get stable. So you react. You gain electrons, you lose electrons, you share electrons, you do whatever you can do to become stable. The only atoms that are not reactive are the ones that we call the noble gases. They're on the far side over here. Helium and neon and argon and krypton and so on, their valence shells are full. Helium has 2 protons and 2 electrons. It only has 1 shell. It's got 2 electrons in that shell. That's all the first shell can hold is 2. So helium's stable. Helium's inert. Helium reacts with nothing. Neon has atomic number 10. 10 electrons, 2 in its first shell, 8 in the second shell. The second shell is full. Neon doesn't react with anything either. We go up to argon. Argon has 18 as its atomic number. 2 in the first shell, 8 in the second shell, 8 in the third shell. Argon doesn't react either. If we don't have a space, if all of our shells are filled up, the atom is not reactive. So here is helium and neon, for example. Totally unreactive. Helium doesn't burn, it doesn't combine with water, it doesn't do anything, it just floats. It just floats. We put it in balloons for one thing, and it floats. We use it to super cool computers, and it doesn't burn or react or anything like that. Neon, we use it for lighting purposes. I'm sure there's other reasons, other things we use neon for, but it also doesn't react. It won't burn, it won't do anything. None of those gases along the side there are going to burn. We often use argon for fire suppression. Especially in computer rooms where you have all these, like in a server farm, you have all these servers there and they get hot. And maybe something ignites and they have argon or krypton or gases pressurized gases, and they release that and it puts the fire out because they won't react with anything. So, but there's only a handful of atoms like that that are not reactive. Most of them are reactive. Hydrogen's reactive, carbon's reactive, oxygen's reactive, sodium is reactive, chlorine is reactive. All of these atoms that don't have their valence shell filled up will react with other atoms. And all they want to do is get more electrons. They either want to borrow the electrons or share the electrons or give up electrons just so they're stable. That's all they want to do. As long as, once the valence shell is full, the atom is happy, if it could be happy. So, like here we have hydrogen, only one electron in its valence shell. It'd like to have a second one. Carbon has 4 electrons in its valence shell. It would like to have 4 more. Now, carbon has an atomic number of 6. It only has 6 electrons, 2 in the first shell, 2 in the first shell, 4 in the second. It would like to get 4 more electrons and become stable. Hydrogen would like to get 1 more and become stable. Oxygen has 6 in its second shell. It has atomic number of 8. 2 in the first shell, 6 in the second shell. It would love to get 2 more electrons to become stable. Sodium, on the other hand, has 11 protons and 11 electrons. And it only has 1 electron in its outer shell. Sodium is perfectly happy in kicking that last electron out there all by itself out of the atom. Goodbye, you're gone. We don't want you, to make itself stable. It's perfectly fine with doing that. Chlorine has 7 electrons in its outer shell, and it readily grabs the electron that comes from sodium. And now it has 8 and it's happy. It has actually physically removed the electron from sodium and put it in the chlorine. So we have 3 types of chemical bonding. We have ionic bonds, which I sort of just described to you, covalent bonds, and hydrogen bonds. Ionic bonds are what we have in salts. If an atom gives up an electron or gains an electron, because it can't do anything with protons. If we gain an electron or lose an electron, we're no longer called an atom, we're called an ion, because now our charges aren't balanced. If sodium, which has 11 electrons and 11 protons, gives up an electron, and we were balanced, we had 11 protons, 11 electrons. If we now have 11 protons and 10 electrons, the sodium is now positive. It's got a positive charge to it. We haven't done anything to the protons, we just have 11 of them. Now we only have 10 electrons. Sodium has a positive charge. It got rid of that lonesome little electron out there in the third shell all by itself, just kicked it out. Chlorine, on the other hand, has 7 electrons in its shell, and it will grab that ion, that electron from the sodium. But now chlorine, which had 17 protons and 17 electrons, now has 18 electrons. Chlorine is also no longer an atom. It's now called an ion, and it has a negative charge. The protons in ions, the protons and the electrons are no longer equal. So in our valence, in an ionic bond, we transfer electrons from the valence shell from one atom to another. Sodium gives up one, chlorine takes it. And now we have what's known as an anion and a cation. If the atom becomes negative, it's called an anion. If it becomes positive, because it's lost an electron, it's called a cation. On our batteries, like in the car battery, the the posts there, the one, if you ever jumped your car, you got a red post and a black post. Anybody? Okay, you're familiar with this, right? So, and you don't take the jumper cables and put them together because that's real exciting. So the red post is called the anode, and the black post is called the anode, and the red post is called the cathode, because that's the positive is red, negative is black. Well, what we're doing here is we're creating an anode and a cathode. The cation is the positive. It has given up its electron. The anion is now negative because it has gained that electron. So now that we've got these charges, these atoms, instead of being balanced, now have a positive and negative charge, and they get attracted to each other like magnets. It's like we call it electrostatic attraction. Anybody ever use a Swiffer? You know what a Swiffer is? You know how you rub it across the floor and all the dust and dirt in the floor, if there is any, comes right, is sucked right up on the fabric of the Swiffer. What happens is, as you push that across the floor, you create a charge on the Swiffer cloth, and that charge then attracts the opposite charge on the dust and dirt and debris. And so that's why it sucks up everything. The only problem with it is it does such a good job. You have to use like a half a dozen of them to get your floor clean, because they work so well, they take up everything. But that's electrostatic attraction. It's a positive and negative charge. Simply by rubbing it across the floor, you generate a charge in the cloth, and it's the opposite charge. It's what's on the debris, and it sucks it up. This is what holds salt crystals together. Sodium and chloride are attracted to each other electrostatically, almost magnetically, if you will, because you have a positive and a negative charge, and they come together, and it forms a crystal. All salts are made up of ionic bonds. Sodium chloride, calcium carbonate, calcium chloride, potassium chloride, all of these different salts that our bodies use show up, are held together electrostatically. Positive cation is attracted to the negative anion. And salt crystals are the result of that. Now, it's not a very powerful bond. It breaks easily. It breaks apart very easily, but that's how we satisfy the sodium. The sodium kicks out its electron, but the electron finds a home with the chlorine or any other atom that wants an electron. It's usually chlorine, but we'll just say it could be any other one too. So the sodium gets rid of its electron, the chlorine needs an electron, it physically grabs it, and then they're attracted together, and we've got table salt. And that's how, and so it forms a crystal, because table salt's a crystal. And here's a very, very busy slide of showing you what's happening. I think the other one was better though. See, because there's the sodium atom, that little white thing is the electron being given to the chlorine, satisfying both of them. But if you want to watch it where it doesn't move, there's the electron going over to the chlorine. Now we have a positively charged sodium ion and a negatively charged chlorine ion, and they're attracted together and give you a crystal. Now, I will tell you that sodium ions are the most important ion in our bodies, because they drive almost everything we do. Chlorine, this is the last time that chlorine gets mentioned, because chlorine doesn't do anything for us. But sodium determines the salt concentration of our bodies. Sodium helps to determine the charge on the membranes of all of our cells that make our cells electrical. So sodium has a big role to play here, and it goes into solution very, very easily. But this is how all salt crystals are formed. It doesn't matter if it's sea salt, it doesn't matter if it's table salt, it doesn't matter if it's as I said, like potassium chloride or calcium carbonate or any of these other types of salt crystals, they're all going to be held together with ionic bonds. Most of the chemical bonding, though, is held together with covalent bonds. Covalent bonds are where the atoms are a little nicer to each other. Instead of stealing electrons, they share electrons. And so what we're going to do is share the valence electrons. So that, the valence shell is where the ones that have the most potential energy. So we will share those electrons. And for part of the time, an electron belongs in one atom's outer shell. And for part of the other time, it's in another atom's shell. And they're held together by this sharing of electrons. And since they're moving at the speed of light, which is 186,000 miles per second, it's like they're always in both sides at the same time. It's sort of hard to wrap your head around 186,000 miles per second. As I saw yesterday that NASA had identified some object. Oh, it was a star that appeared to pulsate, and it said it's very close to us, 4,000 light years away. That's really close. 4,000 light years. A light year is how far light can travel at 186,000 miles per second in a year. That's pretty for a piece. Consider it 6,000 light years. That's not close. That's not any. The moon is close. Mars is close. 4,000 light years is not close. So I guess so in NASA talk, it probably is, when they compare, like to Alpha Centauri or other places. Anyway, the point though is that these electrons are moving so rapidly around their individual nucleus that now they can start traveling around the nucleus of another atom, which they're held together. Sharing these electrons draw these individual atoms together. And as far as we're concerned, the electrons are on both sides at the same time. Sharing two electrons gives you what's called a single bond. 4 electrons gives you a double bond, and 6 electrons is a triple bond. The only atom that we care about with a triple bond is nitrogen. The only one with a double bond that we really pay a lot of attention to is going to be oxygen, because atmospheric oxygen, the stuff we breathe, is O2 held together with a double bond. Everything else is mostly single bonds. With covalent bonding, we can satisfy the valence shell part of the time constantly. So sometimes you're here, sometimes you're there, but you're moving so fast, you're essentially in both places at the same time. Now, there are two types of covalent bonding, either polar or nonpolar. And most of them are nonpolar. This is a covalent bond. Up there on the upper right, we see those are hydrogens. Well, hydrogen only has 1 electron. But if hydrogen shares its 1 electron with another hydrogen, they're both happy. See, they're even smiling. So if they could. Because now hydrogen on the left has 2 electrons, hydrogen on the right has 2 electrons, and they're stable. In fact, this is what atmospheric hydrogen looks like. It's not reactive. Atmospheric hydrogen is much less reactive than elemental hydrogen. Elemental hydrogen is just stuff that blows up and burns. We don't give out toy balloons at carnivals made out of hydrogen. That'd be real exciting, real fast. So, but it's happy because it's got 2 electrons to share, because hydrogen's reactive. Hydrogen would love to react with something, and it won't go not only for itself, it'll react with carbon. Carbon's very good for this. Down here, we see hydrogen and oxygen reacting on the lower left. Oxygen wants 2 electrons in its outer shell. It has 6, it needs 2 more. Hydrogen has one, it needs another one. A hydrogen atom can react with oxygen and they can share electrons. And all of a sudden the hydrogen atom has 2 electrons and you've added an extra electron to the oxygen. And if you bring another hydrogen in to satisfy its need for an electron, now you've got water, H2O. Water is simply 2 hydrogen atoms sharing their 2 hydrogen atoms, each one sharing their individual electron with oxygen. That gives oxygen its 8 electrons in its outer shell, but it also allows the hydrogens to have 2 electrons in their outer shell whenever they want it. And so we create a great deal of stability by doing this. Now, so why do we care? Well, the reason we care about this, and I will tell you that questions about covalent bonding will be very unlikely in any kind of healthcare environment. But covalent bonding gives us the basis of all of the chemicals our bodies use except salts. We use glucose. Glucose is the chemical that we use for energy. Everything we eat that's going to be used for energy is either going to be a carbohydrate, like a starch, converted, broken down to glucose. If you take starch is nothing but 1 billion little glucose molecules glued together. If you eat table sugar, that's 2 glucoses essentially fastened together, and we break that down into 1, and we use it. We use glucose as our source of energy, and glucose is held together by carbon and hydrogen and oxygen sharing electrons. Now, a gram of carbohydrates, a gram of sugar, glucose, gives you 4 calories of energy. Now that 4 calories of energy is the sum total of all of the energy, all the potential energy stored in those valence electrons. So we take it down to that level. Where does the energy come from? When the Snickers bar says 160 calories, or the Coke says 220 calories, or the apple, well, it doesn't say 60, but an apple's about 60 calories, okay? Where do those calories come from? Well, it comes from the electrons. It's a measure of the potential energy from the electrons in the carbohydrates, for example, in the apple, in the Snickers bar, in the potato, in the piece of bread, wherever. And so those calories then reflect the energy in there. And it all comes from the sharing of these electrons. Now here we see carbon in, it's the one in the middle there with the black nucleus. Up there's a carbon atom. It has an atomic number of 6. It has 6 protons and 6 electrons. It has 2 electrons in its first shell, and it has 4 electrons in its second shell. It would dearly love to have 4 more. Well, carbon loves to react with hydrogen because hydrogen only has 1 electron and it wants 2. And carbon will bond with hydrogen to give you 4, it can hold up to 4 hydrogens. And we get CH4, a carbon and 4 hydrogens. This CH4 is methane, natural gas. What do we do with natural gas? What do you do with propane? You start fires. Thank you. What about, that's a good answer, don't get me, we won't go there. Has anybody ever cooked on a propane grill? Okay, yeah, so you're using liquid propane, a gas that you compress down and stored in the tank, and you cook on your grill with that. Or you're a purist and you use charcoal like I do. That's a whole other story. So, but anyway, you burn propane. It has energy in there. Propane has more energy than natural gas does because propane has 3 carbons and more and 8 hydrogens. Yeah, 8 hydrogens. You have more electrons in propane than you do in methane. But methane has potential energy. We burn methane if you have gas heat in your house, if you have natural gas, if you have, around here, they've got natural gas powered school buses and utility vehicles and stuff from the gas company. And for its cleaner, it only gives off carbon dioxide and water. But it has energy. Lots of people use gas to heat their house, heat their hot water, and cook with. If you have a gas fireplace and it's not driven by propane, it's driven by natural gas, and you can burn it. Propane does the same thing. Propane is a little more efficient because it has more potential energy, simply because propane has not 1 carbon and 4 hydrogens, but 3 carbons and 8 hydrogens. Because every one of those hydrogens and carbons brings in potential energy from their electrons. So, it depends on where you live. If you have natural gas, you burn that. If you have a tank in the back behind your house or in the backyard, you burn propane. And if you are all electric, you don't. So, but the energy in a molecule is based on the number of electrons that it's sharing. All that potential energy is stored in those electrons. And this simple carbon and hydrogen a compound like that, we call a carbohydrate. And we don't call methane a carbohydrate, but when we're talking about sugars and starches, we call them carbohydrates. We'll get into that a little later. Okay, now. Carbon dioxide is a little unusual in how it forms. This is another one of those little outliers that uses double bonds. Here, typically we would see this 4-sided structure is very common for in compounds. Here we see a very simple structure. For whatever reason, carbon dioxide holds its carbon and 2 oxygens, and they're both happy because they're sharing their electrons. But for whatever reason, it has a linear structure. It doesn't react with anything. It is filled up, it's happy. The oxygens are in either end. Now, this is a symmetrical structure, and we say it's nonpolar because all of the electrons are distributed evenly throughout that molecule, just like we see in methane. All the electrons are distributed evenly. They're all being shared evenly. The same thing happens here. But sometimes we can share the electrons, but don't share them evenly, and that creates a little bit of a charge on a molecule. Sometimes the electrons are pulled towards the protons a little more than just spinning in orbit around their own nucleus and the other nucleus. Sometimes they're drawn a little closer to the nucleus of the bigger atom. What do I mean by that? Consider oxygen. Oxygen has 8 protons in its nucleus, and hydrogens only have 1 proton. Now, a water molecule has a hydrogen and a hydrogen around the oxygen. It, so I can get this to, oops, let me go back. There we go. A water molecule it's not working. Now the pen's not working. Oh, wait, I can go with this. A water molecule has this shape like this. and it's a very set shape. The angle between the two atoms, between here and here, is a constant 104-degree angle. And it often has been described as looking like Mickey Mouse. So it always has that shape. Let me see if I can get you a better picture of that. Because the way the electrons are attracted to each other. And what happens though is that the electrons on the hydrogens tend to not go in a nice circle around here like this, but they tend to be more elliptical, so they're drawn down towards the nucleus. In fact, all of the electrons tend to be drawn down towards the nucleus because the nucleus has 8 protons and has a big, powerful charge on it. And so a water molecule becomes polarized. The hydrogen ends of the water molecule are slightly positive because the electrons are dragged sort of away. And the oxygen end is sort of negative because it has drawing more electrons down there. We don't change, they still do what they're supposed to do. They're still circling around all the nuclei enough so that everybody's happy. But the charge tends to come to create, it tends to create a charge on the water molecule so that the water molecule is slightly positive on the hydrogen ends and slightly negative on the oxygen end. And let me get back here. And this is important because water holds together through the third type of chemical bond, what we call the hydrogen bond. Really weak bond, but it works very well. Water holds together. You know, if I were to take water and pour it out of the desktop here, it would form a big puddle. It wouldn't just spread all over the place. It would form a puddle, and if this is my sort of service, it would form a puddle. If you take your water bottle there and turn it upside down and turn it back, you're going to have water stuck on the side, running down the side of the bottle. It's not going to all drop down or spread out. Water hangs together. It has great strength together. It will, all the water molecules will hold together and form these bonds. These bonds give water so much strength. You ever, when you boil water, when you put the pan on the stove and turn the heat on, does the water boil instantly? No, of course not. It takes time to get the water to boil. It takes energy to break those bonds in water because they're attached to each other and they don't like to come apart. And so one of the great properties of water is based on these polar bonds where hydrogens are attracted to oxygens and oxygens are attracted to hydrogens. And in our larger molecules like proteins have a 3-dimensional shape, and it's the hydrogen bonding that lets that happen for us. Now, let's see if I can get this thing to work. I wonder if this will play. I don't know why it's not sounding. Okay, I can tell you what's going on now. The hydrogens are sharing their electrons with the oxygen. The oxygen is sharing its electrons with the hydrogens, but the electrons from the hydrogen are being drawn towards the oxygen end. The consequences are the oxygen end of every water molecule is slightly negative, and the hydrogen ends are always slightly positive. You have 2 water molecules together. The positive end of one water molecule will be attracted to the negative end of the oxygen. So the positive hydrogens can be attracted to numerous oxygens of adjacent molecules. Just imagine that it keeps spreading out and spreading out through here. So water holds together. As I said, if I could pour water out across the desktop, it would form a nice little puddle on here, instead of just spreading out and randomly going off into space. And it would stay in that puddle unless it ran over the side, but it would not just break off into individual water molecules because of this attraction that we have here. Okay. So the big three are ionic bonds, which we find only in salts, covalent bonds, which is what most of the chemical bonding uses, and we have hydrogen bonds, which are between positive and negative ends of molecules. It's a slight attraction. It's a weak attraction, but it does give large molecules their shape. Now, the fourth category here is something we only see usually in fats. And this is called van der Waals attraction. Van der Waals attraction occurs when a large molecule briefly rearranges itself, or maybe all the electrons on one side of the molecule flip to the other side, and the molecule is slightly positive or slightly negative, and there's another large molecule next to it that's doing the same thing, and suddenly they're attracted to each other. And then they let go, and then they do it again. It is the presence of van der Waals that causes fats to be solid. Things like butterfat or animal fat are solid at room temperature because the electrons in the various large molecules that make up those fats are slightly attracted to each other. And then let go, they do it again, let go, do it again. But it's enough to give us solid fats and liquid fats. Oils are liquid fats, obviously. They don't stick together. They don't stick together like butter does. Butter is a solid. Even at room temperature, even if it's a little soft and squishy, it's still a solid fat. Animal fat that you trim off of meat, for example, is a solid fat. It's solid because of van der Waals attraction. Now, we don't see the bonds opening and closing and opening and closing, but we know they're there because fat, like even lard, stays solid at room temperature. So van der Waals attraction. It's about, as I said here, has the strength of 1% of a covalent bond. So it's a really weak bond. It breaks very, very easily, but it explains how we have things like fat. Okay. Wish I could get rid of Mickey's head here, but there we go. Okay, now chemical reactions take place whenever we are going to break a bond or make a bond or rearrange a bond. So if we are something as simple as boiling water is a chemical reaction. We are breaking bonds there. Baking a cake is breaking bonds and then making new ones. So whenever we have a chemical reaction, we always start out with reactants, the starting ingredients, and we end up with a product. And the reactants are going to chemically come together. In some cases, you have to require energy to do that. In other cases, they will release energy. If you were baking a cake and you mix together the flour and the sugar and the oil and the eggs and everything else and put it in a pan, let it sit, nothing's going to happen. You're going to have, some interesting bacteria growing on it after a couple days, but it's not going to do anything. However, you can stick that same pan and stick it in the oven and bake it at 350 for however long you have to bake it, and a chemical change occurs. And it converts from all these separate ingredients into a finished product. If you boil water, you can boil water till it evaporates, and you have broken the chemical bonds of the water molecules held together till they break apart and they become water vapor and disappear. You can boil the water out. So we always have we're always going to, in every reaction, we're going to have a reactant and a product. And the product is the end result of the chemical reaction. Now, 3 types of reactions. Synthesis reactions. We are building things up. When we eat protein, we eat a cheeseburger or a piece of fish or chicken or an egg or whatever. We take the protein, which is made up of amino acids. We break the protein down to its individual amino acids, and then we take those amino acids and we rebuild them into a new protein for us. Or we've eaten a lot of carbohydrates and we have glucose. We take that glucose and store it as a polysaccharide called glycogen. We store that in our liver. Glycogen is the human version of starch. It's the human equivalent of what's inside a potato or an apple, the starchy center of that. Those are anabolic reactions. We build things up, and anabolic reactions require energy. Baking your cake is an anabolic reaction. Can't get it to work unless you have energy. Catabolic reactions are decomposition reactions. We break things down and we release energy. If we are burning wood, if we're breaking down, if our bodies are breaking down carbohydrates, in both examples there, we are breaking large molecules into small ones. Anabolic reactions, synthesis reactions take little molecules and make big ones. Decomposition or catabolic reactions take large molecules and break them down to smaller molecules and release energy. In exchange reactions, we're simply changing places with different parts of molecules because they involve both anabolic and catabolic synthesis or decomposition at the same time. And nope, I'm going to stop this. This is a great place to stop when we talk about exchange reactions, because I don't have enough time to explain it any further in detail. So I'm going to stop us. Anybody have any questions before I shut us down? Okay. Any questions on anything?